Hey guys, today is the day we're talking about phase diagrams and their applications to igneous petrology. So first, let me just talk about what phase diagrams are. In igneous petrology, phase diagrams show the composition of minerals that coexist with liquids in terms of temperature and pressure. Using phase diagrams, we can predict the temperature at which minerals will melt or melts will crystallize. And this will be really important when we want to try and predict maybe how a rock formed, what its whole lifetime was in terms of at what depth in the earth it cooled at, or at the surface if it cooled, or why it has a certain texture. And so phase diagrams are super useful in igneous petrology because they help us understand why igneous rocks are the way they are and predict what igneous rocks will form from certain melt compositions and temperature conditions. But before we jump right into igneous petrology phase diagrams with actual mineral examples, let's talk a little bit about something that's probably familiar to all of you, and that is water. Water freezes to form ice, which is its solid, and liquid water is its liquid form, obviously. But a key point in understanding phase diagrams is that we're trying to understand how two different minerals or things affect each other's melting temperatures. And so in the case of this example, we're talking about water as one of those minerals, and we're adding on salt as the other mineral. And yes, water is a mineral, its solid form ice is a mineral. So water is one mineral, salt is the other mineral, or sodium chloride. And these two minerals affect each other's behavior, most notably each other's melting and crystallization temperatures. And so on this diagram, that's basically what is being shown, is how the temperature changes when water is salty. And on the x-axis, what we see is the mole fraction of water in solution. And so that just means that as that fraction becomes smaller, the solution is becoming more salty in the right x direction. So how do minerals affect other minerals' melting temperatures? Well, it's pretty simple. Mixtures of minerals have lower melting points than single minerals. And the same thing occurs for ice. So if ice is present, it's going to take a certain amount of heat to melt the ice. However, if there's salt in the system, that ice will melt a lot more easily, aka the melting point of ice is lowered by the addition of salt. On this diagram, we see salty water in the top right corner, and then ice, or solidified water, and salty water in the bottom left corner of the diagram. And then in between, there's a line labeled liquidus. This liquidus marks the temperature below which ice starts to crystallize and above which water exists only as liquid water. The reason it goes down to the right is because as the salt percent increases to the right x direction, the melting temperature of ice decreases. And so that downward trend is due to more salt. Now let's look at an example. If you didn't understand that, you will now, I promise. Let's take, for example, a 0.95 mole fraction of water solution. This would start here at point A, because we just picked a temperature at which that solution is liquid. So say we start here at A, we're starting at 0.95 mole fraction water, and it's liquid right now, it's salty water. And as we lower the temperature, the ice begins to crystallize once it reaches the liquidus. However, the ice that crystallizes is fresher than that remaining in solution. So the fresh water preferentially crystallizes first before that salty water wants to. So at this temperature where we hit the liquidus at first, it's only fresh water that's crystallizing, leaving behind a remaining solution that becomes saltier and saltier. Therefore, this liquid will follow along the liquidus as it becomes saltier and saltier, decreasing the water mole fraction of the remaining liquid as the pure water continues to crystallize. And this will continue to go down the liquidus given the temperature continues decreasing until the remaining solution becomes so salty that salt starts precipitating out of the solution, and the crystallization temperature is no longer then lowered because the solution is no longer becoming more salty once salt starts actually precipitating out. It's only when salt is dissolved in the water that it keeps lowering the melting or crystallization temperature of that water. In this case, we're looking at the crystallization crystallization of ice. So this understanding of how the liquid changes composition as it starts to crystallize allows us to determine the processes that formed igneous rocks of specific compositions. So let's actually start to look at some real mineral examples now so that we can get a sense for how we can use these phase diagrams. Well, here we have a pyroxene plagioclase, or diopside and anorthite respectively, phase diagram. And in this phase diagram, we can see the two sides. So just as we had more water to the left and more salt to the right on the previous diagram, here we have more diopside to the left and more anorthite to the right. Now, just like salt lowers the melting temperature of ice, plagioclase lowers that of pyroxene, and vice versa. Pyroxene lowers that of plagioclase. Because of this, we can see that the melting temperature of diopside decreases down the liquidus to a certain point, which we'll get to in a second, as well as the anorthite liquidus decreases toward that point as well. Why is it decreasing toward this semi-center point here? That's because the farthest left we can go is the most pure diopside that we can get in this phase diagram. And as we move to the right, we're increasing the anorthite content. The more the other mineral is present, the more that temperature decreases. Similar to that, anorthite decreases down toward the middle because you have more diopside in that direction, more of the other mineral that decreases the melting temperature of your pure mineral. That brings us to the eutectic. The eutectic is really important. It's the intersection between the liquiduses of each mineral. And this intersection marks the lowest possible melting temperature, or the composition mixture that marks the lowest possible melting temperature of a mixture of minerals. So AKA, it's the easiest mixture of those two minerals to achieve. So in this case, the eutectic is around 40 weight percent anorthite and 60 weight percent diopside. This mixture of diopside and anorthite is the composition of those two minerals that is most often achieved when melting mixtures of diopside and anorthite, because it requires the lowest amount of heat or the lowest amount of energy, which Earth doesn't have all that much heat to give away. So it's going to most often melt eutectic compositions or near eutectic compositions of solid rocks. Another important line in this diagram is the solidus. The solidus represents the temperature below which everything is completely solid. Above this, both solids and liquids exist. And you might notice that the eutectic meets, directly contacts the solidus. This further reinforces the fact that it's the first composition to begin forming when melting these solids down here in this lower portion. They're going to start melting at the eutectic composition because when the temperature rises, it's going to hit this, 1280, whatever this is at, before it hits 1400 and can melt this composition over here. So let's take an example. Let's consider a rock composed of around 75% anorthite, 25% diopside. Upon raising the temperature, what composition would the melted liquid be? Well, that depends, because the question could be, once it's all melted, what would it be? Well, obviously it would be 75% anorthite, 25% diopside. But when it first begins to melt, it will start melting with the eutectic composition, which is not the same ratio. Like we mentioned, it's around 40% anorthite and 60% diopside. And this will go on for a while until all the diopside is gone, because like we mentioned, we've only got 25% diopside in the original solid composition. So there's not that much to go before the eutectic composition melt takes all the diopside out of that solid. So once all the diopside has melted, the pure anorthite left over that hasn't melted yet will have to be heated further to continue melting. And as the remaining anorthite melts, the liquid that's forming due to this melting process will travel up the liquidus, because remember we started with the eutectic composition melting, and that was the point where the liquid was in terms of the composition. And then as the pure anorthite started melting, we're traveling to the right on the x-axis, and we have to be traveling up because the temperature is also increasing in order to continue melting the rest of the anorthite. And so we're traveling up the liquidus until the initial composition, or 75 to 25 ratio of anorthite to diopside, is reached. And that's when we know, when we reach reached that initial ratio, that all of the solid material has melted and is now in the liquid because it has the same ratio as the starting material. So we just talked about melting, but let's talk a little bit about cooling like we did with ice. And with cooling along these phase diagrams, we can also start to understand how different textures may arise from different cooling regimes. So if we cool the liquid that we just talked about, so that 75 to 25 ratio of anorthite to diopside, we just melted it completely to its original ratio, and now we're going to cool it. Let's cool it, let's crystallize it, see what happens. So if we start to cool that liquid at T2, temperature of around, I'm going to say that's like close to 1500 degrees Celsius. So at that temperature, anorthite will start crystallizing first, which that crystallized material will move down here to this light gray region labeled liquid and anorthite. And that's because you got the solid crystallized anorthite, but you still have liquid that's still being cooled, and that's not yet crystallized. So this is not solid and this is not liquid, it's a mixture of both. So anorthite starts to crystallize first because we're on this side of the diagram, obviously. And then with that crystallization of anorthite, just as we saw with the salt in the water, because fresh water was leaving the system, the leftover liquid was becoming more salty. Just as with that system, anorthite is leaving the system and the leftover liquid is becoming more diopside rich. Therefore, we're going to move to the left of the diagram because we're getting more diopside rich. And with this, we're moving down the liquidus because remember, we're still lowering the temperature to continue cooling that liquid that we formed to crystallize it. As we move down the liquidus, we eventually reach the eutectic. Once we've dropped the temperature enough and taken out enough anorthite to reach the eutectic composition of around 40% anorthite and 60% diopside, then diopside begins crystallizing, and only then. Up until that point, only anorthite was crystallizing. It's basically the equal but opposite process as we saw when melting. Anorthite melted last after all the diopside had melted. Same as that, but opposite. Diopside's crystallizing last after all the anorthite crystallizes. And at this point, when we reach the eutectic and diopside starts to crystallize, this crystallization is at a lower temperature and will occur more quickly, and that means smaller grains will form. Whereas when we were cooling it really slowly, allowing those anorthite grains to get really big, now we're getting smaller grains that are going to surround the anorthite, creating the finer grained matrix around anorthite phenocryst, or large anorthite class that formed first. So this is going back to the textures we talked about in the igneous textures video. I'll link it up here if you want to check it out. But we talked about how textures change depending on the rate of cooling and crystal growth and nucleation and all of that. And so that video obviously has all that information. I'm not going to go further on it here, but now you can kind of connect how phase diagrams relate to that and how you can visualize as you start to crystallize out a material first, you're going to get those phenocrysts because that's a higher temperature, you're cooling slowly, and then once you reach the eutectic, you're at a lower temperature, you're cooling fast, and you're going to get the fine grained matrix. And that's how phenocrysts and phaneritic and porphyritic types of textures arise. Now let's move on to the quartz and nepheline diagram. I remember learning this in Igneous Petrology, and everybody is always asking, like, why can't quartz and nepheline form together? Well, it's pretty simple. So quartz and nepheline can react in a chemical reaction to form albite. For this reason, albite forms in between their phase diagram. It basically breaks the two up. It's like a line of trees in between your house and your neighbor's house, which is a weird analogy for me to use because I live in El Paso and there's hardly any trees, but you get what I'm saying. So albite is the wall in between quartz and nepheline. So mixtures of albite and quartz can crystallize together, and mixtures of nepheline and albite can crystallize together. But nepheline and quartz cannot, because then they'll form albite. So this relationship creates two eutectics, one in between nepheline and albite and one in between quartz and albite. So a liquid in the quartz side of this diagram would, upon crystallizing albite, move toward the quartz eutectic, and a liquid on the left or nepheline side of this diagram would, upon crystallizing albite, move toward the nepheline eutectic. And these two eutectics actually represent two really common, well, one really common and one not as common rocks in igneous petrology. And these are granite and nepheline cyanide. Granite, you all have heard of, I know you have, and it's not only important for countertops, it's also important for igneous petrology. The eutectic composition of this albite and quartz shared eutectic is the most common composition of granite. It's around 2/3 alkali feldspar, in this case albite, and 1/3 quartz. And that is because of this eutectic here. That's the eutectic composition, and so that's the most often generated composition of granite. Additionally, the most often composition of nepheline cyanide is the eutectic composition seen in this diagram at the nepheline albite eutectic point. So these eutectics represent something major if you understand what this phase diagram is representing. Another nomenclature type of thing that you should probably know is that rocks with composition plotting on the left side of this diagram, or the nepheline side, are called alkaline, whereas those plotting on the right or quartz side are called either subalkaline or tholeiitic. But in general, other than some nomenclature things and the fact that there's two eutectics because albite sits in the middle of the quartz nepheline phase diagram, there's really nothing different between this phase diagram and the one we previously looked at. If you split it in half and read it with just albite and just quartz, or just albite and just nepheline, they read the same way, or you interpret them the same way as we did the previous one. So I'm going to move on to one that is a little bit more different. So this phase diagram is olivine versus quartz, or in our case, we're looking at forsterite, magnesium-rich olivine versus silica or quartz. And in between, we can see there's instatite here. Why? Well, silica and forsterite react to form instatite. So isn't this the same case with nepheline and quartz forming albite? Not exactly, and we'll talk about why in a second. This diagram we can see has a P instead of an E at where its second eutectic should be. However, it's not a second eutectic. It's actually something called the peritectic. And so this phase diagram group, olivine and quartz, have a eutectic and have a peritectic. This is because when instatite begins melting, it produces a silica-rich liquid and a forsterite solid. Because this melting is incongruent, aka it's not melting instatite to create instatite liquid as albite was in the previous diagram. Let me just side note here, albite melts to produce an albite liquid. That is called congruent melting, which is why on the previous diagram they had two pretty symmetrical eutectics. However, here, the in-between mineral, instatite in this case, does not congruently melt. It incongruently melts to produce a silica-rich liquid and a forsterite solid. Because of this, the diagram is skewed and there's a peritectic instead of a second eutectic. However, similar to the double eutectic scenario, if we heat the instatite plus quartz mixture over here, it will begin melting at the eutectic. So if we just look at this part of the diagram, it's pretty similar to the other scenarios we've been looking at. You heat anything of this mixture, you're going to start melting at the eutectic until you melt everything, and then you reach your original composition, whatever side that was on of the eutectic. And likewise, if we melt a forsterite and instatite mixture, it will begin melting at the peritectic over here. And so that's a similar scenario. But when it comes to cooling, let's imagine an example to see how this might work. So imagine a basaltic liquid of position or composition X. So we have an arrow up here and an X here. So there's where our liquid lies in terms of what the temperature of the liquid is at initially and what the composition is at that point. And the composition at that point is around 70% forsterite and 30% silica. We can see this on this x-axis here. And we could also pretty much just call it instatite. As it cools, forsterite forms first, because remember, we said it incongruently melts, in which forsterite is the solid left over, and silica-rich liquid melts first. And remember that cooling is just the same kind of equal but opposite process. So forsterite is going to crystallize first from this liquid. And because forsterite is crystallizing out of the solution, the liquid becomes more silica-rich, moving down the liquidus here toward a more silica-rich composition until it meets the peritectic. Once the temperature has gone down enough and the silica has gone up enough that it reached the peritectic, instatite begins to crystallize. Now, this is really important because forsterite or olivine will often crystallize first occurs in really common igneous scenarios where it then creates these phenocrysts of olivine, like we talked about could happen earlier. So when these phenocrysts form, it's allowed more time to cool, and therefore the phenocrysts get larger. That's why we call them phenocrysts. They're larger than the finer grained matrix. So these olivine phenocrysts form, and then by the time instantite begins to crystallize out of solution, it will surround the forsterite or olivine phenocrysts and create what's called reaction rims around them. So kind of a darkened or altered rim around the olivine phenocrysts. And so you can kind of get a really good sense for how the cooling occurred and what it started as in terms of its composition, depending on if you see these reaction rims around olivine phenocrysts or other phenocrysts in different mineral systems. So all in all, the peritectic eutectic system is not all that different from the eutectic or eutectic systems. Just remember that the fact that instantite, or the wall in between silica and forsterite, does not melt congruently, aka it melts incongruently, is the reason that we have a peritectic or slightly offset eutectic compared to the double eutectic system due to Albite's congruent melting. I hope that makes sense. The last example I want to go through is Albite orthoclase. Albite is a member of the plagioclase feldspar solid solution series, and orthoclase is a member of the K feldspars. So if we look at these diagrams, we can see one has eutectic and one has none. So let's talk about what's happening over here and why there isn't a eutectic and why this thing is labeled M and not E. First, what are the differences between these two diagrams? Well, the one on the left here, or diagram A, is at 0.2 gigapascals pressure. If we change the system and assume it's at 0.5 gigapascals of pressure, we can see that the eutectic shows up and the whole diagram changes quite substantially. So we'll talk about why in a second, but let's consider the lower pressure scenario first, the 0.2 gigapascals, or the left graph. So if we crystallize a liquid at composition X here, this composition is around 55% orthoclase and 45% albite. And what we can see is that if we start to cool it, orthoclase, or potassium-rich mineral, will first solidify out of the solution. And then that will leave the leftover liquid more enriched in albite, or sodium feldspar. And because of this, it will continue to become more sodium-rich and less potassium-rich as that mineral starts to crystallize out, that it follows down that liquidus toward the more sodium-rich side until it reaches M here. What's M and why isn't it the eutectic? So M stands for minimum. Like the other systems, the liquid follows the liquidus to a minimum, and in this case, it's actually labeled minimum rather than eutectic because it's not in contact with a stable, solid resultant like we saw on the previous slide. What do I mean by this? Well, on the previous slide, we saw that the solidus is where everything is solid. It's the same case for here, but instead there's an extra component. Everything is solid in this dark gray region. However, what forms the sanidine solid solution formation upon reaching the minimum is a solid that is relatively unstable. And over time, it converts to the more stable solid forms we can see down in this little bubble down here. And because it's not stable, it's not technically the eutectic, it's the minimum. And so it forms this initial solid that eventually converts to these other solids. The line below which this conversion occurs is called the solidus. So what about the higher pressure scenario, or 0.5 gigapascals, where we see a eutectic now? Why is this? Well, because at higher pressures, more water is dissolved into the liquid. This lowers the liquidus and the solidus enough to where it actually intersects the solvus and now forms the stable two minerals, albite and orthoclase, upon the eutectic composition liquid crystallizing. And so it goes straight to that stable form rather than having that intermediate there. And if you're wondering about how pressure and water content affect magma cooling and melting, we're actually going to talk a lot more about that in the upcoming videos. So here we talked about phase diagrams and in general how to read them, and gave some examples and what the eutectic is, why it's important, and how we can understand textures based on phase diagrams and how things cool and crystallize. But in the upcoming videos, we'll talk about first silicate magmas, in which we'll talk a lot more about gas and water content and pressure and explosive volcanic eruptions because of water and other volatiles in the magma. And then in the following video, we'll talk about chemistry of rocks, and then we've got a bunch more igneous petrology videos coming as well. So look forward to those if you want to know more about that. And again, guys, I'm using one of my favorites, Earth Materials book here, as well as other references that are also down in the description. This one particularly is called Earth Materials, Introduction to Mineralogy and Petrology by Cornelius Klein and Anthony Philpott. And then I also use the Essentials of Igneous and Metamorphic Petrology by Ronald and Carol Frost. This is a really good one. It's also linked in my description if you want to check it out. And that is all I have for you guys today. Thank you so much for watching. Feel free to leave topic suggestions for IgPet or maybe my upcoming Metamorphic Petrology videos in the comments below, and I'll see you guys next time. Bye!